Right, in this video we're going to be illustrating or deriving, however you want to put it, an integral expression that involves harmonic numbers. You'll probably recognize this. This is actually just a slight, well actually, I was about to say this is like a slight representation or a repositioning of the beta function, but it also exists on its own. Now, in case you're unaware, the harmonic numbers is defined as the series of the sum of 1 over k. As k starts at 1, goes up to n. It's a very famous series. It's actually a divergent series, which means that it doesn't converge, obviously. It diverges and actually goes off to infinity. And it shows up in a variety of different applications. It's a fantastic one to have under your belt, in particular, and one that's definitely really fun to explore. Anyway, this is actually a really simple one. There's just a couple of minor things that we just have to be mindful of, but it just requires a very simple series representation of lm of 1 minus x. And then from there, there's just a couple of little slight algebraic elements and repositionings that we do in order to be able to resolve this. Okay, so to start off with, we just bring this negative, which is out the front, and we bring it into the integral. So you'll see here, instead of having negative, the integral from 0 to 1 of x to the n times by ln of 1 minus x, we have the integral from 0 to 1 of x to the power of n times by negative ln of 1 minus x. And the reason why I've done this is because this actually has a very, very nice Taylor series representation centered at 0, or alternatively, a Maclaurin series centered at 0. A Maclaurin series, which is a Taylor series when you center it at 0, or put it about 0 is probably the best way of saying it. Now, there's a crucial bit that we need to keep into consideration when we're using this series. In order for this series representation to be convergent, it requires that the absolute value of x has to be less than 1. So if we're going to use a series representation in this integral, we need to make sure that the region of integration meets those restrictions. And thankfully, because our integral is between 0 and 1, we can see that this restriction, that x has to be less than or equal to 1, it actually slightly diverges, but its limit to go to 1 is convergent. So we are actually allowed to use this for this integral. If, however, the integral was, say, from 0 to 2, we would not be able to use it over the elements that are greater than 1 because it diverges. Okay, so all we're going to do is we're going to plug that into our integrand. So I have m, which is, as we had before, the integral from 0 to 1 of x to the n times by negative 1 minus x dx is equal to the integral from 0 to 1 of x to the n. And as you can see here, we've just replaced it with its Maclaurin series representation. The series from m equals 1 to infinity of x to the power of m divided by m dx. So all I'm doing here is going to employ the linearity property associated with continuous integrals, which says that the integral of a sum is equal to the sum of the integrals. So we can draw the sum out the front. We see here that this 1 over m component, which is from here, is just a constant. So once again, the linearity property associated with integration of continuous integrals allows us to draw it out the front. And we then have the integral from 0 to 1. We have this x to the n term multiplied by x to the n, which, just using our basic indices laws, becomes x to the power of m plus m dx. Now, whenever we're doing integration of x to the power of something, we need to be mindful of whatever values the actual sign we do have to be mindful of the sign, but we need to be mindful of the special case that is associated when the power is equal to negative 1. Because if we take the integral of x to the power of negative 1, it does not follow the conventional rule of, if you have x to the power of k, it's x to the power of k plus 1 over n. When we have 1 over x, that's a very special case, and the integral of that becomes ln of x. So we just need to be mindful of that when we're going through. Here we know that n is a natural number because of harmonic numbers, the minimum value is n is equal to 1. So we've got this is 1, and we know that the minimum value of m is equal to 1. So the minimum value it can take is x to the power of 2, so we don't have to consider that special case of x to the power of negative 1. We can just use the standard formula associated with integrating a, I was going to say polynomial, but it is a polynomial, but a monol or something like that. Either way, x to the power of k. And so, as I said, we just use the simple rule. The integral from x to the power of k is equal to x to the power of k plus 1 divided by k plus 1, which is what we have here. This 1 on the m obviously just remains at the front, and this series remains there as well. So plugging in the upper bound and the lower bound, we can see this is really simple. When we sub in 1, we've got 1 to the power of m plus 1. 1 to the power of n plus m plus 1, which is just 1. So Remember that n and m are integers, so this is going to be 1 to the power of an integer value, which is just 1. So that's 1 for the upper bound. And for the lower bound 0, we have 0 to the power of an integer, a positive integer at that, which is very important. It's not important for the other one because it does not matter if it's a negative integer, but for 0, it is important to know, well, it's absolutely crucial that we identify that the power that we're raising it to is positive. Because it's negative, that becomes 1 over 0 to the power of something, which goes to something very, very different. But with it being a positive power, we know that 0 to the power of something positive is just 0. So the upper bound is 1 and the lower bound is 0, so forget the 0, and the 1 just becomes the 1. So we're just left with the upper bound here, which becomes the integral from 0 to infinity, 1 on m times by this component, which putting it all together is what we have here. The sum from m equals 1 to infinity of 1 over m times by m plus 1. Now, although we've already covered this, just to be 100% safe, remember that we can never divide by 0. So here we need to make sure that m plus 1 will never be a 0. If it is a 0, then we have to consider that as a special case and deal with that. As we went through before, the minimum value of n in this case is 1. The minimum value of m in this case is 1. So therefore, minimum, 1 plus 1 plus 1 is 3. So we will never have a division by 0. But just remember, whenever you're dealing with anything of this nature, just always keep track of those things, because the number of times, especially when I was first diving into problems like this years and years and years ago, especially when I was doing my undergraduate mathematics and in high school, where I wouldn't even think of that, and then we would do visualizations of the solution and there'd be these huge discontinuities and I could not understand. So now I'm probably, I wouldn't say hypersensitive, you need to be hypersensitive. So when I say hypersensitive, I don't mean that in a negative way. Anyway, gosh, I go on. Okay. So what we're going to do now in terms of evaluating this sum is we're going to take this component and we're going to apply a partial fraction decomposition. It's very simple to do. And so this expression here, which is what we've got here, is equal to 1 over m plus 1, 1 over m minus 1 over m plus 1. So I'm just going to apply that to this sum and we'll be able to resolve our solution. So I of m, which equals the sum from m equals 1 to infinity of the expression that we had before, is equal to the sum, m equals 1 to infinity, replacing it with this partial fraction decomposition, which is what we have here. Now remember, this sum is with respect to m, so this 1 over m plus 1 can be drawn out the front, and we're left with what is remaining within the brackets. And so what I'm now going to do is I'm just going to separate this out. We know the sum of a of n minus b of n is just equal to the sum of a of n minus the sum of b of n, which is what we have here. So I've just separated it out into its individual terms. Okay, so when we have a look at this term here, we can actually separate this out into different integrals. So starting from m equals 1 to infinity of 1 to the m and adding them all up means that that's exactly the same as going from m equals 1 to n plus 1 and then going from m plus 2 to the rest, onwards on to infinity. So all I've done here is I've just split up this sum into two separate summations, from m equals 1 to m plus 1 of 1 over m, and then the next term, which is m plus 2, going all the way to infinity. Equally, if we take this sum here within it, and we want to replace it, instead of having 1 over n plus m plus 1, if I just want to have it in the form of 1 over m, and I'm doing that deliberately so we have a consistent form, well, look, for every individual term that involves m, we're adding the same quantity, n plus 1. So at the minimum value of m is equal to 1, this starts off at n plus 2, and then it just increments up by 1 and 1. So instead of having this in this form, we can replace it with this form, which means that instead, if we have 1 over m, this starts at m plus 2, and as I said, if you don't believe me, just plug in m is equal to 1 into this, and you will see that you get n plus 1, which is n plus 2, and then obviously as we go off to infinity, it just goes off to infinity as well. Now, I've done that very deliberately because then we can cancel off these two terms. We see that they're exactly the same. And so what we're left with then, out of having two infinite series, we actually have a finite series. And this 1 over m plus 1 remains the same, so nothing has changed from that. That's what we drew out the front before. But now we have the sum from m equals 1 to m plus 1 of 1 over m, which, if we look at our definition of the harmonic numbers, is just a harmonic number when it's evaluated at n plus 1. So instead of using 1 over k, we've just got 1 over n. But as you can clearly see, if we put in n plus 1, we have this expression here. So we have 1 over n plus 1 times by the n plus 1th harmonic number. Putting it all together, that becomes h of m plus 1 over m plus 1, which is the desired quantity. So, very simple integral in this case. This was one that was actually put on a integration page that actually run on Facebook. So I'm not going to name the person who put it on because I haven't got his permission yet. But yeah, thank you very much for that suggestion and for putting that question up. I've absolutely had a great time doing it. For anyone watching, if you like this, please like the video. If you want to see more videos like this, please subscribe. If you have any requests, please either comment here or send me a direct message, and if I'm able to solve it and I have time to do it, I certainly will. Otherwise, I look forward to seeing you all in the next video. Okay, goodbye.